Okay, so 1-1, let's check how the stream is going. Yeah, looks like I'm up. Cool. Checking the quality of the sound. Yeah, so far so good. Okay. Yeah, let me try to enable. I would like to check to see the chat as well. Yeah, how can I do that? Oh, so I'm notified that I'm live. That's actually pretty good. How can I see? Maybe option quality. Yeah, higher picture quality. So let's use a higher picture quality. Okay, I think I see the chat. Fine. Yeah. So what we'll be doing today, guys, it's trying to solve Advent of Code day 17. So this will be a pretty interesting challenge. So let's see how far we'll go. So what's the idea? So day 17, I managed to finish outside the stream the code for day 16. I think day 15. I did it on stream. So as I've read on Reddit, another application, looks like it's shortest path algorithm we'll need to implement with some tricks and optimizations. Yeah, let's read first the problem and try to unfold it and see we'll be able to solve it or not. So far I've got 30 stars. It's by far my record. Last year I think I solved only 5 problems, so this year 15 or so, assuming it's 15 points. So yeah, let's dig right into the problem and see what can we do about it. Will we manage to solve it or not? As always, seems pretty interesting, but we'll see. So yeah, day 17, Clumsy Crucible. The lava starts flowing rapidly once the lava production facility is operational. As you leave, the reindeer offers you a parachute, allowing you to quickly reach Gear Island. As you descend, your bird's eye view of Gear Island reveals why you had trouble finding anyone on your way up. Half of Gear Island is empty, but the half below you is a giant factory city. You land near the gradually filling pool of lava at the base of your new lava fall. Lava ducts will eventually carry the lava throughout the city, but to make use of it immediately, elves are loading it into a large crucible on wheels. The crucibles are top heavy and pushed by hand. Unfortunately, the crucible becomes very difficult to steer at high speeds, and so it can be hard to go in a straight line for very long. To get Desert Island, the machine parts it needs as soon as possible, but you'll need to find the best way to get the crucible from the lava pool to the machine parts factory. To do this, you need to minimize heat loss while choosing a route that doesn't require the crucible to go in a straight line for too long. Fortunately, the elves here have a map, your puzzle input, that uses traffic patterns, ambient temperature, and hundreds of other parameters to calculate exactly how much heat loss can be expected for a crucible entering any particular city block. For example, so we have this input, a bunch of numbers. Each city block is marked by a single digit that represents the amount of heat loss. If the crucible enters that block, the starting point, the lava pool, is the top left city block. The destination, the machine parts factory, is the bottom right city block. Okay, so bottom right. Because you already start in the top left block, you don't incur that block's heat loss unless you leave that block and then return to it. Okay, so if we pass through it again after, then we'll consider it. So for now, no. Because it's difficult to keep top heavy crucible going in a straight line for very long, it can move at most 3 blocks in a single direction before it must turn 90 degrees left or right. The crucible also can't reverse direction after entering each city block. It may only turn left, continue straight, or turn right. So left, continue, turn right. So this means it cannot go backwards. So it's like only a 90-degree turn. Okay. So we go 2, then 1, then we rotate. We go right, then up, right, down, right, down, right, down, 3, right, down, another 3, left, down, right, and we exit our map. This path never moves more than 3 consecutive blocks in the same direction and incurs a heat loss of only 102. Directing the crucible from the lava pool to the machine parts factory, but not moving more than 3 consecutive blocks in the same direction. What is the least heat loss it can incur? To begin, get your puzzle input. Okay, so we've got a problem. I guess for now we'll need to try to understand it a little bit. For this, let's try to use a whiteboard. So I've had prepared this whiteboard. Just a moment, need to switch this. So yeah, I was thinking on how we can solve it. So it's not a lot of like algorithms to find the shortest path. So Bellman Ford, one could be second Dijkstra. We were reading it Dijkstra before, but it's Dijkstra. Looks like that will be the correct form. So Dijkstra. Maybe A star algorithm as well can be used. But we have this trick. So besides that, we need to find the shortest path. So we need to minimize as well the heat loss. So yeah, let's try to emulate a little bit this graph and have a feeling of what we're dealing with. So for this, let's use the whiteboard. Yeah, let me remove Dijkstra for now. Maybe we'll use it, maybe not. We'll see later on. Okay, so kind of on the left side we have our points. So here, and on the right side we have the best path. So maybe let's try to write it down. So assuming we are here in 2, so this will be our node. So what's the options in our case? We can go into 4, 1. I guess there are two options only, so we can go either into 3 or into 4. But 3 as well has in itself two options. Moving right. Backwards we cannot go. It's specified. So it can go either down, which will be a 3, or can go right, which will be a 2. So we kind of will need to take in consideration somewhat this structure. Okay, so 4 itself can go into 1 or can go into 2. If we choose 1, then it can go only into 3 and can go down to 5. To 5. If we choose 2 here, it can go again bottom 2, or can choose to go into 5. So I guess this will be our 2 if we chose it, and we can go either here. Wait, yeah, I confused myself a little bit. Okay, so we choose this 2, so 2 can go 4 and 3 only. It's no other option. So because we cannot go right, it's pointless, and up, it's upper bound. So yeah, let's draw it again. So we have 2. We are at this stage. We either can go into 3 or into 4. If you go into 3, so we are here at this level. If we go at this level, we can go into 3, one more bottom, or into 2, this one. So if we are at this 3 level, I guess it will be this one. We move 1 down, will be another 3, and could be like on the right side, it could be a 4. So here we have like 3 2. 3 2 will be this one, so it will be 1 2 again, so either 1 or 2. Let me go here, 2 and 1, and this one. So if you go with 4, I try to draw it in the form of like a wave. So this will be like some sort of a breadth search algorithm. We try to form a wave and then find the shortest path through this wave. At least try to. We'll see. Yeah, so 2 1. Yeah, let's add 1 here. If it's 4 goes into 2, and 4 goes into 1. 1 goes into 1, or 1 goes into 3. So kind of we know that we have the direction. So we start at this top left, and we can go only right or down. We cannot go diagonally. We need to understand why we chose 4. So for example, if we go if we go here, so if for example we are at this level, we have 2 and 5. At this level we have like another fork. It will be like 2. Yeah, okay, so 3, this will be like 3 3 2 2 3 3. Yeah, I'm not sure if I'm doing it right. Yeah, let's try a little bit different approach. So let's try to take 3 points right away. Because we may have this kind of configuration. So what's better to choose? From 4 1 3, or could be like 4 1 5, 4 1 1, or can be like 2 3 3, 2 3 3. Not really, but 3 3 3, actually 3 3 3. And we have like 4 2 1 as well. So yeah, what I'm trying to do, it's starting at 2. What are the possibilities by going 3 nodes? Because we may have like all 3. So this configuration. We may have this configuration down. We may have like 2 up and 1 down. Yeah, only this is possible. And we may have like 1 and 2 like this, and this kind of in double. So let's try to write all sums for these cases. So for example, for this, so we'll have like 4 1 3. For bottom one, we'll have like 3 3 3. Yeah, now let's do combos in this form. So we have like 4 1 4 1 1, this one, 4 1 1, 4 1 1. So it'll be one combo. The second will be like 4 2 1, 4 2 1. So what else is possible for us at this stage? Yeah, we may have 3 3 2, and 3 3 2, 3 2 2 2. Yeah, may have like a down. Wait, I'm a bit confused. So we can have 3 3 3. Okay, we put it. We may have like 3 3 2, 3 3 2. Yeah, we have this, and we may have like 3 2 1 as well. So we go down. No, but yeah, we change direction, so it's not possible actually. Yeah, it's not a little bit clear for me, because we have like 3 in one direction, so from 2. So I assume the direction will be either this or this. So right, but we don't care. But yeah, if we go down, then we need to switch, so we can go 3 more than in this case. Yeah, Okay, so that's interesting because my idea is somewhat in those lines. Because if we go full down, so it will be like 3 down. We've got it. So if we go 1 down and then we switch left, then we'll need to have like 3 2 1 5. But yeah, I'll use tuples of 3 only. It will be like 3 2 1, or we can do 2 down and 1 left. It will be like 3 3 2, 3 2 1, and 3 2 3 2 2, 3 2 2. What else can be? Yeah, I think it's all. So yeah, fast sum 4 1 3 will be like 8. Yeah, let me switch color. Looks like I cannot switch. Yeah, small. Why did I do that? I don't think I need to do it. Okay. I need to close this, and let's close this as well. We don't need it. So yeah, still I cannot. I don't know why I cannot change color. Yeah, maybe I need a new layer. Yeah, let's add a new painting layer, and then yeah, okay, looks like this works. But strange. Maybe it's a bug. I think it's a bug in Paint. Okay, once again, so we have like this. Yeah, let me use it. So it will be like we start here. So we'll have all the 4 ones, and we have like 3 3 3, and we have like 3 2 1, 3 2 1, and we have like next 3 3 2, 3 3 2. So this will be our results. Okay. Yeah, I don't know why it doesn't work. Yeah, anyway, so here we'll have like 7, not 7 but 8. This will be 9, this will be 8, this will be 7, this will be like 6, and this will be like 8. So going greedy, it's not helpful. So we need to find the shortest path, but I guess yeah, we'll need to dig into how to implement like a Dijkstra algorithm. Yeah, probably it's time to move and try to find some examples on the internet on how to solve Dijkstra, implementing Dijkstra. Okay, so we have all of our nodes. F11. Yeah, switching to the browser. pretty strange. So even if I choose the browser, it doesn't want to show. Why is that? Oh, because I have this enabled. Okay, so now it's not enabled anymore. Okay, let's get back to our stuff. We don't need this, and we need to find out Dijkstra. We have all the routes, all the nodes. The distance from 0 to 1 is 4. The minimum distance from 0 to 2 is 12. 0 to 2. Yeah, minimum distance. Okay. 0 to 3. So how is this implemented? Dijkstra using adjacency matrix. The idea is to generate a shortest path tree with a given source as a root, maintaining an adjacency matrix with two sets. One set containing vertices included in the shortest path tree. Other set includes vertices not yet included in the shortest path tree. Yeah, looks like so much. Oh my god. I will be banned by YouTube. But I mean, what can I do? So yeah, create a set, SPT set, shortest path tree set that keeps track of vertices included in the shortest path tree, whose minimum distance from the source is calculated and finalized. Initially, this set is empty. Assign a distance value to all vertices in the input graph. Initialize all distances values as infinite. Assign the distance value as 0 for the source vertex so that it's picked first, while SPT set doesn't include all vertices. Pick a vertex U that is not there in SPT and has a minimum distance value include U to SPT set. Then update the distance value of all adjacent vertices of U. To update the distance values, iterate through all adjacent vertices for every adjacent vertex V. If the sum of the distance value of U from source and the weight of edge UV is less than the distance value of V, then update the distance value of V. Okay, so let's see step number 1. We'll try to go like step by step. To understand the Dijkstra algorithm, let's take a graph and find the shortest path from source to all nodes. Okay, so something like what we have. The set SP set is initially empty and distances assigned to vertices are 0, infinity, 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 infinity. Okay, so we need to understand how many vertices we have. So in our example, it's not that easy to do though, because or is it though? We have some constraints. So the constraints sit on the phase that we cannot like use more than 3 blocks in the same direction for our shortest path. Okay, so I think for me it will be like interesting to solve it. So we have like JavaScript here. And we have graph. From this point to this point, we have this code. Okay, so overall it's somewhat clear. Yeah, looks like it will be like a pretty long night. I didn't implement Dijkstra. I don't think I ever did it. And we have like a small complication as well. So besides Dijkstra, we need as well to have this limitation. Okay, so I guess let's divide this problem into chunks as what we'll do. Imagine we'll receive a task at work to do it. So we need to find the vertices or to produce the graph. But how we'll be producing the graph, I think it's somewhat the work which I did. Okay, but so we have the weights from source to node 1. Okay, so I guess in our example, we'll have so yeah, probably, so first stage I want to understand what's the graph plot. So yeah, let's get back to our drawing board. And here, yeah, looks like I didn't change it yet. No, it should be. So we are on our drawing board. So assuming we have like how many? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's quite a big graph. And here will be like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's a 12 by 12. Oh my god, that's a quite big starting example. Maybe we should choose something smaller, but 12 by 12 will be like 144 vertices. And I guess edges. So all the edges will be like a binary tree, because they cannot be formed in any other way. So the graph will look like something on those lines. So for vertex 0, so let's assume we are here at index 0, but we have a point like 2, but it's ignorable, I assume. We do not take it in consideration. So from 0 we go to node, I guess we'll mark it like 0, 0. So we go to 1, 0, and the value of this will be like 3. From 0 to 0, 1. From 0 to 1, the path will be 4. From 4, yeah, we have a link to 0, but I guess direction, it doesn't really important for us now. But maybe it will be later on. Okay, so let's continue with drawing more. So let's assume we want to have a link between 0, 1 and 1, 1. I mean 1, 0 between this. So 1 0 and 1 1 and 2. So it will be like 1 1. So the weight will be 2 for this. So from 1 0 to 2 0, I guess this will be another 3. Another 3. So from 0 1 to 1 1, we have a link. From 0 1 to 1 1, and value, I guess it's 2. So if I want to get from the source to 1 1, I have like two options. Either go through 0, it will be like 3 2, or this path. So it's better to go through 3 2. Yeah, let's continue to expand our tree. But anyway, it looks like it's a binary tree. It cannot be anything else than that. So 0 1, 0 1, it's 4. So next one will be 0 2 here. And the cost of 0 2 will be like 1. So from 0 2, I can go to 1 2. I can go to 1 2. And the cost of this will be 1. Or I can go to 0 3. And the cost will be like 3. This one. Okay. So we have our tree. It's in the form of a binary tree. So let's assume we want to arrive, so it's not this one, maybe we should expand a little bit, but let's assume I want to get to this 5. So this will be our final point from source to 5. So 5 will be like 3 1. So 3 1 we can come from 0 3. This will be like 3 1. No, it will be like 1 3. Sorry, not 3. 1 3 the position, and we'll have the price 5. Or we can get from 1 1 from 2 from 1 2. Here as well will be 5. So what's our option? We want to arrive to 5. We can go this path, or maybe we'll have like another path which arrives to 3 5, something like this. I don't know, maybe start going this direction. Something like that. But assuming we have this configuration, what will be the shortest path between 0 0 and 5 5? So either we go through this route, like let's do it, it'll be like 3 plus 2, and then we could get another 2, then plus 1. Either we move plus 3 or plus 1. So here it's kind of clear that we'll need to go with +1. So what's the path from 0, 0 to 0, 1? Okay, similar as we do have in our example. From 1, 1, 0, 2, and then from 2, 1, 2, this will be like 1, 2. And then 1, 2, and then this will be like 2, 5. So I guess that will be the structure of nodes. Though how can we check if we move into the same direction? How can we check if we move into the same direction? Simplest way, I think it's everything down. I'll put, so if we'll make a binary tree or some form of binary tree, we'll have like source, left side will be down, and everything on the right side will be like left. Yeah, but at this level we may have like not only a binary tree, but we'll be able to move into multiple direction as well. Vertices. I don't know, I guess stage 1 will be to create a graph. This will produce like not only 144 vertices, but even more. As each one in the middle will have like points or links in all directions. So I guess start will have only left, right, left, down. Middle ones will have all directions. How can we represent that? At the end of the day, it's still like still an adjacency matrix. But wait a minute, maybe we are given already the adjacency matrix. Because we have like a starting point, and this will be like from 0, 0 to 0, 1, it's 4. From 0, 0, but no, because kind of this will imply we'll have connections everywhere, so this needs to be transformed. So we'll be transformed something like this. So we have like 0, 1, 2, 3, 4. Let's assume, and bottom side 0, 1, 2, 3. So 0, 0. We'll put a 0 because it's no cost. So from 0, 0 to 0, 1. Yeah, we do have a link, and we do have a cost, so it will be like 4. From 0, 0 to 0, 2. No, we don't have anything. But if we go the other way, yeah, in this case it will be like 2. So from 0, 0 to 1, 0, we'll have like 3. Here will be less structure. The link between okay, so from a node 0, yeah, but this will be like 0, 0. If I mark it like that, makes sense. So it's a triple level matrix or what? Yeah, cool. Yeah, I've got a problem like I do not have a lot of ideas on how to solve yet. Yeah, probably it will be some time to reflect. I've got a problem like okay. So we try to identify our graph. Have had troubles to do. Here we see a shortest path.